Okay, till now what we have done? Do you all remember? Do you all remember? Till now what we have done? Number of microstates. Microstates between what? 0 to E for free particle. Clear? What we found finally, the number of microstate between 0 to E was how much? I think this is what we have got, 4 pi V divided by 3.
Pi 3, H naught cube.
H naught. It was H naught. H naught cube.
Cube.
E to the power
2m e to the power 3 by 2.
3 by 2. Basically, it was what? Volume of phase space. Basically, how you get this? Total number of microstates for a single particle will be equal to the total number of what? Cells, basically. Which was basically this. Volume divided by 4 by 3 pi r cube is 4 by 3 pi r cube is for the what? Phase space, and V is for the volume of what? Of your coordinate. Clear? Now today let's do one example. Let's consider one example. Now for a single particle of mass, what? Single particle of mass M is in volume V. Clear? Now find the number of accessible microstate. Find the number of accessible microstates between E and E plus dE. Now how to get this? This is your example. Now how to do this? Now this is very simple. Till now what you have got, for a single particle you have got a total number of microstates between 0 to E. Now we have to find the number of accessible microstate between E to dE. Now what do we do? That is basically given by omega. Let's write omega E. Basically it's given by a derivative of this. Clear? It's very simple. Is basically given by what? Your derivative of this. Why derivative? Because it is between E and dE. So what was the total number of microstate if it was from 0 to E? From 0 to E, it's basically this much. Total number of accessible microstate. Now between E to dE is basically given by this. Is it clear?
Yes, sir.
Now what we have to do, we have to just differentiate. What was your phi? D by dE of 4 by 3 pi V 2me to the power 3 by 2 divided by H naught cube. You have to take a derivative of this. Everything is constant, so we can take it out. 4 by 3 pi V divided by 2m to the power 3 by 2 divided by H naught cube into derivative of e to the power 3 by 2. So what is the derivative of e to the power 3 by 2? What is the derivative of e to the power 3 by 2?
3 by 2. 3 by
2
3 by 2
e to the power half. Is it clear?
Yes,
sir.
It will be half. So 3 will cancel out. 2 2s are 4. Clear? So basically you'll end up with what? Total number of microstate between E to dE is 2 pi V by H naught cube Clear? 2m to the power 3 by 2 e to the power half times of dE. Clear? Is it clear?
Yes, sir.
Yes, sir.
So we are getting additional dE. Do you remember why we are getting additional dE? Do you see that additional dE? Do you see that dE? Why we are getting that dE
Yes,
is
sir.
basically why? Because we are basically taking what? d phi by dE. Clear? This d phi by dE, what we can write? Instead of writing d phi, because this is the number of accessible microstate in what? Number of microstate in dE. Clear? So this dE we write this as omega. So this dE will go over here. Is it clear? Is it clear?
Yes, sir.
So finally we'll end up with this additional dE which is sitting over here. Something which is sitting over here times dE. Is it okay? Is it fine?
Yes, sir.
Okay. So don't forget about dE. Now, if you want to find the total number of microstate, what you will do? You'll just integrate this, because this is what phi is basically d phi. This omega is basically d phi. Now, if you integrate this from 0 to e, if you want to get all the accessible microstate between 0 to e, then how much you will get? You will again end up with what? Exactly integration of this will be what? From 0 to e. Will be basically what? On the left hand side, you will get phi. Clear? For the energy, this is the total number of microstate between 0 to e. Let's write it as phi e. Clear? This will be exactly whatever you got, 4 by pi v, this h naught cube 3 times of 2me to the power 3 by 2. So you'll again end up with the same value. This is a total number of microstates between 0 to e, and this is a number of microstate, accessible microstate or some microstate between e to e plus dE. Basically, it's in the range of this, where this is the size of this is dE. Is it clear? Now let's go with the fundamental postulates. Mental postulates. Postulates of statistical mechanics. So this following are the postulates, or basically laws of statistical. Basically, these are the fundamental. Number one is all gas under consideration. All gas under consideration is considered to be composed of large number of what? Large number of molecules which are constantly moving. Moving and behave like small elastic sphere. Clear? So what does the first postulate tell you is, let's say, I'll just make it in 2 dimensions so it will be easier to see. Now, if you consider there a certain box, or in this case a rectangle, and inside that is filled with what gas? Now what does your first postulate tell you is that all of the gases are made out of small molecules, clear, which are moving all over the place, clear. Now, which behave like an elastic sphere. Why it behaves like an elastic sphere? Because as soon as it collides, it again recoils back. Clear. If it was inelastic, then your total energy would have been lost due to inelastic collision. So we want our energy also to be conserved in a sense. Clear. So the collision are perfectly elastic in nature. Now your second postulate is all the cells are of equal size. Are of equal size. Whatever the cell, each compartment, and each compartment comprises of small cells, and all of the cells are what? Made out of equal sizes. Now third is a very important. Now third is very important law which tells you all accessible microstates corresponding to possible macrostates are equally probable. All the accessible microstate corresponding to possible macrostates are equally probable. Previously, we were talking about a prior probability. A prior equal probability or something? Do you all remember? It is basically that. If we consider n number of cells, then the particle being found in each and every cell, a single particle found in every cell has a equal chances or has a equal probability. Clear? A particle to be in any one of the phase space is any one of the cell is what? Is same for all the cell. Clear? Is it clear or not?
Yes, sir.
Now let's consider. We have what? 4 distinguishable particle. Distinguishable particle A, B, C, D, which are in 2 cells. They are in 2 cells. What? 1 and 2. Let's call it. Now we have 2 cells, and according to second law, each cell should be of equal size. So let's consider a particular microstate. Let's consider this microstate. All the particle A, B, C, D are here, and 0 particle is here. Now the probability of microstate is how much? Microstate is how much? 4 particle are here, so it will be what? 1 by 2 to the power 4 is 1 by 16. Do you remember the total number of microstates was given by something like this?
Yes, sir.
So from this also you can get probability n factorial divided by something. Do you remember? N factorial, n minus n factorial times of p to the power
n q to the power n minus 1.
N minus r, I think. N minus n. N minus 1. N minus n, I think it should be. No, n minus. Yeah, it's fine. N minus 1. So this should be small n. This should be small n. If you do exactly how much you will get? 1 by 2 to the power 4. Because half for each and every. One particle will have a probability of what? A will have a probability of half either being here or here. Clear? And we are using and. A and B and C and D are over here. So that's why we have to multiply all the probability. Half into half into half into half. Clear? So it is basically what? 1 by 16. Clear? Is it clear or not? Now
Yes,
let's
sir.
consider the second scenario.
Yes, sir.
Probability in microstate, which is given by A, B, and C, D. A, B, and C, D means A and B could be here, and C and D could be here. This particular microstate. For A, it will be how much? Half. B, it will be half. And there is or C and D. So that's why it will be how much? And this and this should be. So it will be half times of half.
Sir?
Again, you will end up with what? 1 by 16. Is this point clear or not?
Yes, sir.
Because either this also has to occur simultaneously with respect to this and this. So that's why we are multiplying this. So similarly for, again, you can see A, B, C, and D. It should be how much? 1 by 2 into 1 by 2 into 1 by 2 for this side. And similarly for half, again, it will be 1 by 16. So all the probability of the microstates are what? For a given macrostate is what? Is same. Clear?
Yes, sir.
Now your third point is, from this we can know that, again, from this itself we got the definition. The probability is proportional to omega E. Probability is proportional to omega. Do you remember? First, this C will be given by what? This is just a constant, P to the power something into Q to the power, if you remember. That C will be basically this one. The probability will be proportional to your what? Thermodynamic probability or your total number of microstate. Now, fourth is your what? The equilibrium state of a gas corresponding to the macrostate of maximum probability. Is it clear or not? Is it clear or not? All the probability of all the microstates
Yes, sir.
are same, but what about the macrostate? Will the probability of all the macrostate will be same or not? It won't be for the macrostate, if you remember. Do you remember? Because let's consider this two particle A, B, and no particle is over here. And the second possibility is A and B, and also what? B and A could be here. So this two macros corresponds to what? 1, 1. And this corresponds to what? 1 and 2 and 0. And similarly, this one corresponds to what? 0 and 2. If you can see over here, how many do we have? 1, 2, 3, 4, 4 number of macrostates, and possibly number of microstates are what? 2. Clear? For this macrostate, total number of microstate is 4. So for this one, the probability is high. For this one, probability will be how much? 1/4. For this one, it will be 1/4. So probability of macrostate may vary, but the probability of microstate is same. Clear?
Yes, sir.
Now we consider equilibrium state. So what do you mean by the equilibrium state? The equilibrium state in statistical mechanics is basically considered as a macrostate with maximum probability. In this case, this example, your equilibrium state will be given by this macrostate. Clear? 1 and 1, because this has a maximum probability, which is half. So that's why this is considered as a equilibrium state. Now we move on to what? Your fifth. For a given box, the total number of particles is fixed. number of particle is fixed. This is basically the conservation of number of particles. This is conservation of total number of particle. This is a conservation of total number of particle. If you remember, it's basically n1 plus n2 plus n3. Do you remember something up to n?
Yes, sir.
N will be equal to n, summation of all n's. This is your conservation of number of particle. Now, finally, what do we have? The total energy. The total energy is what? The total energy of the system is constant. I think you all remember N1 E1 plus N2 E2 plus N3 E3, so on and so on, will give you the total energy, if you all remember.
Yes, sir.
So this is a conservation of energy, conservation of number of particles, and we learned about what? Equilibrium state and what? The probability in microstate, equal prior probability, that is called. And after that we talked about what? Cells, size of the cells, because the size of the cells are same, so that's why the probability will be same. And each and every all the gases which is contained inside the box is made out of elastic sphere, which is called a molecule. Is it clear?
Yes, sir.
Now let's do this topic of density of quantum states of energy of particle. Basically, this is a density of state. Density of what? Quantum state. Do you know about degeneracy? Degeneracy?
Yes, sir.
What is degeneracy?
Sir, it different state with the same energy.
Good, exactly. Let's consider a particle in a box in quantum mechanics. The energy over there will be given by what? Pi square h card square divided by 2ml, length of the box, into n square, basically proportional, where n will be given by what? Let's write this as constant k. Let's write this as, okay, not k, let's write this as c, into nx square plus ny square plus nz square. The ground state is given by what? Nx is equals to ny is equals to nz equal to 1. So energy will be how much? Basically 3c. Clear? Is there any other possibility by which we can bring it down to 1? Because the lowest number is 1. I think that we can't. Because if you put 2, it will be how much? 4. Now let's consider another. When nx is equals to 1, n2 equal to 2, n3 equal to 1. Clear? Now the total energy over here is how much? 1 plus 4 plus 1, 4, 5, 6, 6c. Now exactly same energy, how we can get? We can get by what? Considering nx is equals to 2. Is it clear? Ny is equals to 1 and nz equal to 1. With this also you will end up with what? This was ny and nz. You will end up with what? 6c. And exactly after this, what we can consider? Nx as 1, ny as 1, and nz as 2. With this also you will end up with how much? Same energy. Now, for a given state, how many? There are three different such values which will give you a same energy. So that's why it's called degenerate. For this case, it's called three-fold degenerate. Degeneracy. Threefold degeneracy. Because they are having three such configuration or which will give you the same energy. For a given state, there are three configuration because the energy states are given by this. Let's consider this as a first excited state. How many we are getting? Three such configuration to give you the same energy. So that's why it's called a threefold degeneracy. Now, if the energy are non-degenerate, what we can do? Just like a ground state is what? Called non-degenerate, because there is only a single configuration. If the energy level are degenerate, there will be a very large number of quantum state contained in dE. Let's consider a small energy level dE between E and E plus dE. Then what? There will be a large number of quantum state between these two range. Due to this degeneracy as well also. We have to take in consideration that also. It is represented, the number of state is basically represented by what? Density of quantum state. Density of quantum state, which is denoted by Z. Please remember, it's very important, it's denoted by Z, which is a function of E. Now these are the available quantum state per energy range at a given energy E. Clear? Now the density of quantum state is defined as a number of quantum state per unit energy range at a given energy. For a given energy, per unit energy, how many number of quantum state do we have? That is basically given by what? Your density of state. Number of state per unit energy. Now, as you have already seen, this is exactly similar to what? This is exactly similar to what? Total number of microstates, if you remember. So ZE we can basically write as 2m by, instead of h naught, we'll have what? H cube. Clear? 2m to the power 3 by 2 e to the power half times of d. Have you seen this expression? Exactly for the classical we have done. Instead of h, we had h0. So that's why I did that example previously. d phi by de, if you remember. This will give you exactly this. Now, this is for a density of state for your quantum state. Now, if you consider the spin as well, so the spin could be either up or down, which is given by plus minus half. Do you remember?
Yes, sir.
Spin up or spin down? In chemistry also, I believe you have done.
Yes, sir.
So how many possibly there are?
Plus minus half.
In addition to that, we have two additional. Here, it will be 2 times 2 pi by h card 2m. So that's why you will multiply by 2. Is it clear? This is with spin, this is without spin, because the spin will add one more additional state for each and every state. So that's why it will be doubled. Is it clear till here?
Yes, sir.
Yes, sir.
So now if you want to find the number of particles, this gave you how dense a particular state between a particular energy level was. Now if you want to find the number of particles in that state, let's say we have considered E and E plus dE for a certain energy level. Now we know the density of state for this is given by what? GE. And let's consider a spinless or spin with spin also. Actually, it doesn't matter. And we want to find the number of particles having energy which in between these two. Basically, in number of particles having energy dE. Then how do you get it? Now, number of particles in energy dE will be given by what? GE FE times of dE. Clear? This is number of quantum states. And what is FE? FE is basically a distribution function. Is it clear?
Yes, sir.
This is how you find what? The number of particles which are occupying these quantum states. This is usually how you do. This is usually how you find. Total number of will be given by what? I think this we have done it previously. If you do you all remember? Do you all remember? Suppose let's consider a situation where a particle are equally distributed everywhere. Then basically what this Fe can be taken as 1 because the distribution is uniform all over the place. So number of particle will be given by what? Density of state. Clear? Just remember this. Number of particle between the energy level E and E plus dE is basically given by what? GE density of state times their distribution function, because the distribution functions will tell you how it will be distributed over the energy range. That also you must know. Clear? Because over certain range, let's consider over this range, the number of particle may be more. Clear? Over here, the number of particle may be less. So this is your distribution function. Now multiply by how many number of states are there. Density of states will give you the number of state. Is it clear now?
Yes, sir.
Is it clear? Now one type of distribution function we have done. Do you remember what kind of distribution function we have done till now? What kind of distribution function we have done till now, if you remember? Any guess? Binomial.
Yes, sir.
And from that we got Poisson's and
Gaussian.
what? Gaussian. Clear? So today what we have done? We have basically done the postulates of what? And in addition to this, just for your Stirling approximation we have to do. Stirling's approximation. This is just a mathematical, you just need to know. Ln of n factorial will be given by what? N ln of n minus 1. Minus or plus, I think it should be minus. Because sometimes you have to take a factorial of n. So that's why at that time it will be very helpful. For time being, I'm taking n to be 100. Which is giving you what? For n equal to 100, log of n factorial will give you how much? 363.74. Now n log of n. Now I'll just find n log of n1 minus 1. Which is giving you n log of n minus 1. Over here, it's giving you 459.517. Now it's different. Now, if we increase the value of n substantially, for 1000, it's coming out to be difference of n log of n minus n. Sorry. It's basically n log of n minus n. Okay. I'm extremely sorry for that. For 100, it was coming 363 and it will give you what? 360.517. Now, if you see, both are roughly close. Now, if we take this value to 1000, then how much we are getting? For these are the two tables. Let's consider. Here we have log of n factorial. Here we have n log of n minus n. Sorry. So this for over here n equal to 100. How much we got? 363.74, 360.517. Now for 1000, how much we'll get? 5912 over here and 5907 over here. Now you can see that both are really closing together. For 10,000, how much I'm getting? It's getting 8210, 8.9, and over here 8210, 3.4. Now that's why it's called a Stirling formula. So this is approximation where n is very large. And all of you, you just remember this formula. It will be very helpful later. Is it clear?
Yes, sir.
So I think we must stop here. So we'll continue to